algorithm design. Okay, so let's think about combinatorial problems. And as you probably all know, there are certain types of problems like sorting and shortest paths for which we have optimal polynomial time algorithms. That means polynomial time algorithms are guaranteed to output the optimal solution in polynomial time, even on worst case instances. Okay, so some problems are easy. However, many combinatorial problems, for many combinatorial problems, we do not have such strong performance guarantees. Okay, and these include problems like data clustering, partitioning problems, subset selection problems, pricing problems, and so on. These are all hard problems that were technically NP hard. So we cannot hope to have universal, efficient algorithms that will do well on worst case instances. And moreover, for many of these problems, in practical applications, different methods work better in different settings. And also, there is often a very large family of methods that one can try to use in practice. Okay, so given this, it's very natural to try to use machine learning to kind of automate the algorithm selection or algorithm design for these problems. So in other words, it's natural to try to use data, examples of typical instances coming from a domain and machine learning in order to learn an algorithm that does well for our specific type of data instances. Okay, and this is what I call data-driven algorithm design. Now, this type of approach has been long used in many different fields. For example, has been used in artificial intelligence, in computational biology, and in mechanism design. And in fact, several breakthroughs in this field have come from this approach. However, until recently, basically, there have been no formal guarantees for this approach. Okay, and this is something that I've been working on recently with my students and our collaborators. Okay, and just want to give you just like examples of types of results you can try to prove, so not going into details. So just first, let me mention how you can kind of phrase the algorithm selection problem as a statistical learning problem. And by the way, this formulation is due to Tim Ravgarden and his former student Rishi Gupta. They introduced this recently in an ITCS paper and the corresponding journal version. Okay, and here, the formulation here is really natural. So we fix a problem that we want to solve, and this can be, say, facility location or clustering. And then we also fix a large, potentially infinite parameterized family of algorithms for the given problem. Okay, and then what we do, we take samples of typical instances coming from the given domain. This will be technically IID instances coming from the underlying distribution of our typical instances. And then, of course, we use this sample of typical instances in order to come up with an algorithm that we hope does well on new instances coming from the same domain or the same distribution of our instances. Okay, so very natural statistical learning formulation, and of course, this crowd knows that we can hope to provide very general sample complexity guarantees for such scenarios, and for example, we can hope to give uniform convergence bounds, right? There should be epsilon or epsilon squared depending on the agnostic or realizable case. Okay. Now, so this is you can naturally fit such algorithm selection into a statistical learning framework. The only challenge that appears, the interesting challenge that appears when you think about algorithm selection problems is that now the corresponding cost functions have a very different structure than what we are typically using in machine learning. So in particular, because of the combinatorial natures of the outputs, in these domains, if we fix an instance and vary the parameters of the underlying algorithm family, we can have sharp discontinuities, like in these pictures here, okay? And so that's a challenge that we have to overcome, but it turns out that you can overcome this challenge, and in our own work, we looked at several different types of problems and several algorithms families for those problems, and we're able to analyze the pseudo-dimension of this algorithms family. So for example, for clustering problems, we look at parameterized families of procedures, or we first do linkage followed by dynamic programming. We also looked at how to initialize the Lloyd's method. So we have a infinite parametric family of ways to initialize the Lloyd's method, and we also can analyze the pseudo-dimension of that. We also looked at ways to round semi-definite programs, so parametric families surrounding semi-definite programming algorithms for problems that can be written as integer quadratic programs, like MaxCut. We also have works in the mechanism design context for like generalized VCG auctions and other item pricing mechanisms for multi-buyer scenarios. You can also try to learn how to branch, or you can also learn how to align sequences, so lots and lots of applications, and you can even write general theorems in terms of the structure of the dual functions, which is what we've been doing more recently. Okay, and I have 30 seconds left. I just want to mention that you can also think about the online learning version of the problem, and this becomes even more exciting technically. Why? Because, as I mentioned, the corresponding cost functions have sharp discontinuities, and in the worst case, you might not be able to achieve no regret, as we all know, for example, even for learning threshold functions. So, for example, in a Fox 18 paper, we identified the sufficient condition on the corresponding cost function, something that we call no dispersion. So that is sufficient for achieving no regret. So roughly speaking, we impose that the discontinuities of the corresponding cost functions are dispersed. They are not too concentrated. And then that's sufficient to achieve no regret. And we show that for many of those algorithms family that I mentioned, under natural conditions, either about the algorithms family or about the input instances, the corresponding cost functions are dispersed, and so you can achieve no regret. Okay, and overall, I just want to mention to finish by saying that I think that this is a really exciting, really exciting area. There are many interesting technical questions from a learning theory point of view, and of course, the implications in algorithm design can be very exciting. Because this is actually how people do use algorithms in practice these days. They tune hyperparameters, and they use machine learning and data, and so it's cool to have formal guarantees for this approach. Okay, so I'll stop here.
Just a quick question for Nina while the next speaker